Now we turn to Quicksort. It sorts in place with no second array by splitting the work around a chosen pivot. Quicksort has one main move called partition. Pick a pivot value. Rearrange the array so everything smaller sits to its left and everything bigger sits to its right. Then recurse on each side. Think of a room of people. Pick one person as the pivot. Everyone shorter stands to their left, everyone taller to their right. After that one sweep, the pivot is in their final spot. First we choose a pivot. This version always uses the last element. That is the CLRS Lemuto scheme. Then we partition. After one pass, the pivot sits in its final sorted position, and it never moves again. Then we recurse on the left part, and the right part on their own. Unlike merge sort, Quicksort does no extra merging. The partition step does all the real work, and the recursion just walks to smaller pieces. Pivot choice can go wrong. Suppose the pivot always lands near one end. That happens when the array is already sorted and we always pick the last element as the pivot. Then the tree turns into a line. Each partition peels off only one element and hands down the rest. This array of 6 needs 5 levels, not log base 2 of 6, which is about 2.5. Look at what that lopsided tree costs. Each level peels off only one element, so this array of 6 needs 5 levels, not log base 2 of 6, which is about 2.6. That is exactly what produces Quicksort's big O of n squared worst case, and the common mistake section makes it concrete with real comparison counts. Predict, then reveal. Quicksort with the naive endelement pivot on already sorted input with n equal to 8. Roughly how many total comparisons? Pause and guess. The answer is 28, which is 8 times 7 over 2. Each partition peels off one element and scans the rest, so the comparison sums 7 plus 6 down to 1. That is the big O of n squared triangle, and the instrumented run later measures exactly 28. Let's read the partition pseudocode, the Lemuto scheme. The pivot is the last element, A at index high. We set I to low. I marks the boundary of the small region. Everything from low up to I minus 1 is already less than or equal to the pivot. Then J scans from low up to high minus 1. For each J, if A at index J is less than or equal to the pivot, we swap it into the boundary at I, then move I forward by 1. When the scan ends, we swap the pivot into index I, its final slot, and return I. Quicksort ties it together. If low is less than high, we partition, which gives back the pivot's position P, then we sort the left part, low to P minus 1, and the right part, P plus 1 to high. Let's partition this array, step by step. The pivot is the last element, 10. J is the cursor that tests every element once. I is the boundary of the small region, the values that are less than or equal to the pivot. Each row is the array after we test A at index J. Both cursors start at index 0. J equals 0. I at index 0 is 38, which is greater than 10. So no swap and I stays at 0. Nothing in the array changes. J equals 1. I at index 1 is 27, still greater than 10. Again no swap and I stays at 0. J equals 2. I at index 2 is 43, still greater than 10. No swap, I stays at 0. So far no small values have been found. J equals 3. I at index 3 is 3, which is less than or equal to 10. This is the first small value. We swap it into the boundary at index 0, the amber cell, and I moves to 1. J equals 4. At index 4 is 9, also less than or equal to 10. We swap it into the boundary at index 1, the amber cell, and I moves to 2. J equals 5. A at index 5 is 82, which is greater than 10. So no swap and I stays at 2. The scan is now done. Final step. We swap the pivot 10 into index 2, the amber cell, its final sorted slot. Everything to its left is less than or equal to 10, and everything to its right is greater. We return 2. So how many comparisons did this one partition make? A learning check on cost. How many comparisons does one call to partition make on an array of n elements? Pause and answer. The answer is exactly n-1. The for loop tests every element from low up to high -1 against the pivot exactly once, no matter how many swaps happen along the way. Swaps vary with the data. The comparison count does not. Here is partition in C. It takes the array in a range, low to high, and returns the pivot's final index. The pivot is the last element of the range, A at high. And here is the invariant, written as a comment. I is the boundary. Everything from low up to I-1 is already less than or equal to the pivot. The loop walks J from low up to high-1. Notice it stops before high because high is the pivot itself. If A at J is less than or equal to the pivot, it belongs in the small region. So we swap it into position I and move the boundary up by 1. After the loop, everything before I is small and everything from I to high-1 is large. So we swap the pivot into position I, which is its final resting place. And we return I. That element never moves again. And here is the recursion that uses it. The base case. If low is greater than or equal to high, the range holds 0 or 1 element, so it is already sorted. Otherwise we partition, and P comes back as the pivot's final index. Now look at this guard carefully. We only recurse left if P is greater than low. Because P and low are unsigned, P-1 would underflow to a huge value if P were 0. That guard is not cosmetic. Without it, the program reads far outside the array. Then we recurse on the right side from P plus 1 to high. The pivot at P is excluded from both calls because it is already in place. The full program is in the Quicksort file, and the note there spells out that same unsigned underflow reason. Let's see the same partition at 3 levels of detail. The concept, the pseudocode line, and the C line side by side. Reading across each row shows one idea in all 3 forms. The first row is the scan. Whenever a value is less than or equal to the pivot, we swap it into the growing small region at I, then step I forward. The pseudocode and the C line say exactly the same thing. The second row is the finish. After the scan, we drop the pivot right after the small region. That spot is its final sorted position, and we return I. Here is what those 3 levels add up to. The pseudocode names the invariant that I is the small region boundary, and the C shows that invariant being maintained with 1 comparison and at most 1 swap per element. It is a single left to right pass, so partition is big O of n per call. Let's tally Quicksort's cost. On average, it is big O of n log n random pivots split the array roughly in half, giving a balanced tree like merge sorts. The worst case is big O of n squared, a pivot that is always the smallest or largest element, as on already sorted input with this last element rule, produces the lopsided tree we saw. Quicksort is not stable, but it is in place, using only big O of log and extra space for the recursion stack.